So good morning. So regarding the DSDV module 4, in the last period, we were discussing analog inputs, and we saw the working of the microphone, accelerometer, fluid flow sensors, and gas detector. And regarding the analog inputs like the keypad, knob, and position encoder, microphone, accelerometers, and fluid flow sensors that we have seen. So next, we'll see the next topic called as ADC, analog to digital converter. So basically, we can find two types of ADCs. So one is flash ADC, and second one is successive approximation ADC. So now let me discuss regarding flash ADC. So one of the simplest and most widely used ADC is the flash ADC. So here we see the figure. So we have the input voltage Vin. So this Vin is the analog input signal or voltage. So that needs to be converted to digital form. And we have one more voltage called as VF. So this VF is the reference voltage. So basically you have two voltages. One is Vin, analog input signal voltage. Second one is the reference voltage. So this Vin is nothing but the voltage, analog input voltage, analog input signal that needs to be converted into digital form. And VF is the VF is the reference voltage. So this analog input signals from the sensors. So the input signals from sensors needs to be converted into the digital form. So for that reason, we have the use of these ADCs, analog to digital converters. So like using these ADCs, you can process the analog signal so that the digital output can be fed to the digital circuits and embedded softwares. So the basic element of this ADC is a comparator. So you can see here 1, 2, 3, 4, 5, and like a number of comparators have been used here. So you can see the dashed line here. Okay, so we have a continuation of the resistor connection as well as the use of comparators. So the basic element of the ADC is the comparator, which will sense so whether the input voltage at the positive terminal of this op amp. Okay, so whether the input voltage applied at the non-inverting terminal is above or below some reference voltage. Okay, so this reference voltage is applied at the inverting terminal of all the op amp, so which can act as a comparator. Okay, so the basic function of this comparator is to sense so whether the input voltage Vin, right, applied at the non-inverting terminal of comparator is above or below a reference voltage applied at the negative terminal here, as I'm showing here. Okay, and this comparator will be able to output us a 1 output or a 0 output accordingly. Okay, and the simplest form of ADC is what you're seeing here is a flash ADC. Okay, and again you can see that the output of these comparators, okay, output point of these comparators are applied to the encoder circuit, and this encoder circuit will be able to generate the fixed point binary value. Okay, so the main advantage of this flash ADCs are that they're able to convert an input voltage to the digital form so very quickly. Okay, like as the name flash indicates, so these ADCs are very much fast. Okay, so high speed flash ADCs can perform tens or hundreds of millions of samples per second. Okay, so they're suitable for converting high bandwidth signals. Okay, so for this reason, these are very much widely used. And according to the figure, so what you can see here, so you can find here the series of registers used. Okay, like this forms the MSB register and this forms the LSB register, which is connected to the ground. Okay, and the register nearer to the reference voltage is the MSB register, and this is the LSB register. Okay, so we have used a series of registers, and this register is forming as a voltage divider network. Okay, and like here I can assume that so we have 8 number of registers: 1, 2, 3, 4, 5, 6, 7, 8. And as we're having a dash here, so means we have a series of registers here also. And you can assume that here we have used 8 number of registers. Okay, and if I assume this V reference as 5 volts, okay, so this VF for the reference voltage assumed as 5 volts, and we have 8 number of resistor connected, so which is forming as a voltage divider network. So we have used VF is equal to 5 volts, and we have assumed the 8 resistors have been connected. So then the current flowing in the resistors that can be measured. Okay, why? Because the voltage drop across across each and every resistor according to the use of Ohm's law. V is equal to IR, where V is the voltage drop across across the resistors, and I is the current flowing through the resistor, and R is the value of these resistors. Okay, with respect to ground. So the last resistor nearer to the ground. So what I'm showing here. So the last resistor near to the ground will have the least voltage drop. Okay. Similarly, the next resistor above the first resistor, like this one, it will be having more voltage drop. Okay. And so on until the last resistor. Okay. So what I mean to say is the upper resistor will have more voltage drop here, okay, when compared to the last resistor with respect to the ground. So regarding the working, so if I assume this, suppose if the applied analog input voltage Vin is equal to 3 volts, so this 3 volts is applied to all the non-inverting terminals of the comparator, like as I'm showing here. So this Vin is applied to the non-inverting terminal of all the op-amp as a comparator. Okay, right? So this Vin of 3 volts is applied to the positive terminal or the non-inverting terminal of comparator. Okay, suppose if this 3 volt is greater than the resistor tapping voltage, so then the output of comparator will be equal to 1. I repeat, suppose if the 3 volts applied at the non-inverting terminal of op-amp is greater than the voltage voltage across the resistor tappings, so then the output of comparator will be equal to 1. Okay. So now if you see the next comparator, say for example, is last but one comparator. So here the input voltage is applied as 3 volts to the non-inverting terminal, and here is the resistor tapping voltage, right, at this particular point. So which gets applied to the inverting terminal. Okay, so whether here, so this 3 volt is greater than the resistor tapping voltage. Okay, this is based upon the resistor value actually. Okay, so based upon the resistor value used here, you have some amount of voltage that gets applied to the inverting terminal. Okay, so here this 3 volts may be greater than the resistor tapping voltage. Therefore, based on the resistor value we have used, all the comparators will be able to give us different values. Okay. Okay. So therefore, say some comparators may give output as 0, and few comparators may give output as equal to 1. So the like these down comparators are LSB and upper comparators are the most significant bits. Okay. So you can say that the lower 3 comparators will give us a high output, and upper 3 comparators are able to give us 0, 0, 0 output. So like these outputs of the comparators are being given to the encoder circuit, and the encoder will give output in terms of the digital form. Okay, so like this you can explain the operation of this flash ADC. So the next question is, why do we use this flash ADC? So this flash ADC is the simplest possible ADC, and it is very much fast. and immediately you have the conversion of the analog input voltage Vin to its digital form. Okay, so you can explain these points, and same points have been given here also. Okay, so regarding the next parameter with respect to ADC is the resolution. So what is the resolution basically? So this resolution will depend on the number of registers used. Okay, so if we use three registers, so then we have only 3 bits, right, at the output point. So the resolution will be less. So if the number of bits are more, that is the number of registers and the number of comparators are more, so then the resolution will also increase. Therefore, the resolution of ADC will depend on the number of bits, and in turn will depend on the number of comparators, and in turn will depend upon the number of registers. And generally you can find here 8-bit ADC to be used. So next is successive approximation ADC. So next kind of widely used ADC is successive approximation ADC. So this successive approximation ADC is used because the earlier flash ADC, what we saw in the last slide, so that flash ADC was using so many resources, like we had used 8 number of registers, so which were acting as a voltage divider network, and we had used 8 number of comparators, and we had used 1 encoder. Okay, so basically the flash ADC is not economical. Why? Because it will be using so many resources like 8 number of registers, 8 number of comparators, and 1 encoder circuit. Okay, so the basic point here is the flash ADC is not economical. So, but advantage, what we saw in the flash ADC was the conversion will take only 1 cycle. Okay, so the main advantage of flash ADC was like it was very much fast, right? So fast conversion was possible because it took only 1 cycle for the conversion of analog input voltage to its digital form. So, but our successive approximation ADC will take 8 cycles. Okay, like even though we have more number of cycles to be used, so for the conversion, so but still the number of resources are very much less in case of this successive approximation ADC. As you can see here, so only 1 comparator is used, and so 1 DAC is being used, right, along with the register called as a successive approximation register. SAR stands for successive approximation register. Like even though like this is an ADC, so but still we need to use a DAC. Okay, right, inside the ADC that we'll be using a DAC, and similarly you can find here two number of voltages. So one is Vin, and second voltage is the VF. Okay, so this Vin is the analog input voltage, and this VF is the reference voltage. So you can see the circuit. So this SAR, a successive approximation register, has a start control signal. Here it is. Okay, so this SAR has got a start control input signal. So when the clock is given to this, it will start. Okay, so this start control signal is basically used to initiate the operation. Okay, and it is in turn activates your DAC, as you can see here. Okay, so the start signal applied to the SAR will in turn activate the digital to analog converter here. So you can see this. So this ADC has got a built-in DAC. Okay, so we have this input voltage Vin. So this Vin input. So this Vin input is applied to the comparator and VF, right? So this VF is a reference voltage. Is applied to the DAC, as I'm showing using the mouse. So this reference voltage is applied to the DAC. Okay, and that will give the analog output. So this analog output is again applied to this inverting terminal of the op amp, okay, or comparator. So this op amp is used as a comparator. So the comparator will compare this input voltage Vin, okay, so with the converted analog input signal of the reference voltage. Okay, So when the start button is on, so the SAR is initialized. So to the value 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. So like the decimal equivalent of this binary number is 255. Okay. So when the start input is on, the SAR is initialized to the value. The initial approximation will be 0 followed by 7, 1, 2, 3, 4, 5, 6, 7. Yeah, 7 number of ones. Okay. And this is equivalent to 255. So this value is entered from the SAR output to the digital to analog converter, and the negative input of the comparator here. Okay, so suppose if the comparator gives output value 1, okay, so this comparator will be able to give the output as 1 if this bin is high. Okay, suppose if this input voltage is high, okay, so this comparator output will be equal to high or 1, right? Similarly, the comparator will be able to give us 0 output if Vin is less. So output given by the comparator, we call it as D7. Okay, so the comparator output gives D7, right? And this will be equal to 1 if Vin is higher than the initial approximation. Okay, and if and this becomes 0 otherwise. Okay. So if this Vin is greater than this initial approximation, so then output is equal to 1. So this 1 or high will be approximated as D7 as 1. D7 as 1. So the next approximation will happen with D7 equal to 1 and this particular 0 and all ones. Okay, so this D7 and this 0. Okay, suppose if one bit is 0, so then it will be half the value of 255. Okay, suppose if this next bit, okay, so called D6 bit is equal to 0, so then this will be equal to half of the initial approximation, where initial approximation was 255. And if this D6 bit is assumed as 0, means suppose if this bit is equal to 0, so then it will be half of this 255, that is equal to 126. So now this bean is compared with 126. Okay. So next comparison is done with this D6 bit. So if Vin is greater than 1 followed by 0 with all these ones, so then output is equal to 1. If not, output is equal to 0. So whatever will be the output, this will be going back as D6. See here. Okay, so whatever will be the output, this will be going back as D6 and stored in the SAR. Okay, with the D6 bit. Okay, and that is given here. D7, D6, again followed by 0, again followed by all number of ones. So this will happen 8 number of times up to the D0 bit. Okay, so after the 8th cycle, so from D7 to D0 bit, okay, all this bit will be stored in the SAR. So once this happens, so then this done bit, okay, so then this done bit will be activated. Okay, so this done output bit is activated. So then same D7 to D0 bit will be outputted, and so this D7 to D0 output will be outputted as D outline, So hence analog input will be able to convert it into the digital output in terms of zeros and ones. So the only problems what you can see here will be is that it will take 8 number of clock cycles. Okay, so one clock cycle for each bit starting from D7 to D0. Okay, like this will take 8 number of clock cycles. So for the conversion, so the main advantage what you can see here is So we need lesser number of resources when compared to the flash ADC. And the same thing can be seen here. Here we have only one SAR register and only one DAC is used and one comparator is used. So when compared to the flash ADC, where we had used 8 number of comparators, 8 number of registers, one encoder, etc. Like in this case, SAR successive approximation ADC. So we need less number of resources. So one SAR is used, so one DAC is used, and one comparator is used. So the main demerit here is the time taken is more. Okay, so when compared to the flash ADC, the successive approximation ADC will take 8 number of clock cycles. Okay, hence the time consumed is more. So you can take the help of this particular figure, and these are some statements like using which you can explain this. So next is LED indicators. So now let's see the next topic. Let's support LED indicators. But this is acting as one kind of output devices. So these light emitting diodes or LED indicators will be acting as one type of output device. So these LEDs are used as indications to show whether the system is on or off, okay, or the system is having some error or not, or if the system is busy or idle, etc. So to have the indication of the status of a system, so for example, a system is on or off, or we have the encountering of error or not, so whether the system is busy or idle, etc. So to exhibit or show such indications, we can go for this output device support LED indicators. And these can also be used to indicate the system is okay or not. Okay. So if you know that, so when current is passed through an LED, it emits light, hence the name light emitting diode. So if LED is used as active low output, okay, suppose this LED is used as an active low output, so then like this is the figure you can make use of. So the current will flow from the positive, like actually plus VCC or high potential, so via the resistor and through this diode, light emitting diode, and active low port. So the current will be flowing from high to low potential. Okay, so the LED will be able to glow, right? So the LED will be able to operate and glow or in the on condition if and only if the LED is in the forward bias condition. And as you can see here, this anode potential is greater than the cathode potential. Hence, you can say that so this LED is in the forward bias condition. Hence, we can expect the flow of current. Okay. Yeah. So we also have an equation here. So the equation for current is I is equal to plus V minus B LED minus BOL divided by R. So where is plus V is the plus VCC applied here. Okay. And this B LED is the voltage drop across the LED, and VOL. So this VOL is the output side voltage divided by R. So what is R here? R is the resistance value used here. Okay. So by increasing the current, you can have the increasing in the brightness of the LED. Okay. Yeah. Yes. Same thing has been explained here. Okay. So next is 7-segment LED display. Okay. So in the last, like we have seen an individual LED. Okay. In case of the 7-segment LED display, circuit is as shown here. So we have this common anode type of LEDs used here. So where the anodes of all these light emitting diodes starting from A to G along with the decimal point that has been shorted here, right? So all the anodes are been shorted and been given to the plus VCC. Okay. So here each digit has a common anode or common cathode. So we can go for the common anode configuration, or we can go for the common cathode configuration. So the circuit shown here is of common anode type. Why? Because all the anodes are been shorted and it's been given to the plus VCC. Okay. Suppose if I use the common cathode configuration, means like I'll be shorting all the cathodes of all these LEDs, and that will be given for the ground. Okay. So, but as you can see here, like this configuration or this circuit is using common anode configuration. Why? Because all the anodes of the LEDs have been shorted, and that has been given for the plus VCC. Okay. So we have a common anode for all these LEDs. Okay. And this A, B, C, D, and A, B, C, D, E, F, G are the individual segments of a segment display, like as you can see here. Select let's say this can be one segment, A segment, B, C, D, E, F, G segment along with the decimal point. Okay. So the circuit is of common anode type. Why? Because all the anodes have been connected to the plus VCC. So hence here four number of 7 segment LEDs are connected together. See here, 1, 2, 3, 4 number of 7 segment LED displays have been connected all together. Okay, like it also has a dot. So this small dot. Okay, as in here. Okay, so one LED meant to show this decimal point, right, or the decimal point or the dot here. Okay, but this can also be used for displaying the floating point numbers. Okay, along with A segment, B segment up to F segment. See A, B, C, D, E, F, G. So you can also go for this decimal point, and this is basically used to have the displaying of the floating point numbers. So you can see here, so each 7 segment display is commonly connected to this A bar, B bar, C bar, D bar, E bar, F bar, G bar. Okay. So here each and every 7 segment display is commonly connected via these lines to these signals A bar, B bar, C bar, D bar, E bar, F bar, and G bar, along with the DP, where this DP stands for the decimal point. Plus, we also have this A0 bar to A3 bar. So these A0 bar to A3 bar signals are used to activate the particular LED, like using this PNP transistor. Okay. So we have this A0 bar to A3 bar, A0 bar, A1 bar, A2 bar, A3 bar, used to activate the particular particular LEDs. So as we can see, all these 7 segment LEDs have been connected to each other. If all these A0 to A3 bar are made active low, as you can see here, so this A0 to A3 are active low signals, and if A0 to A3 bar are all low or all made low, so then all the LEDs will be on. Okay, so why are this? PNP transistors? Okay, so we can select the particular LEDs using this active low input signals, and if all these are made 0, 0, 0, 0, so then we have these LEDs to be selected. Means all the LED, all the 7 segment displays will be selected. And you can see that A bar to G bar lines, means A bar, B bar, C bar, D bar, E bar, F bar, and G bar lines are common for all the LEDs. Okay. So like in which the basic point here is, so the same A bar to G bar lines are common for all these LEDs. In which LED I want to display selected or activated from these lines using this A bar, A0 bar to A3 bar. So by pulling this any of these lines low, okay, so I can select the particular LEDs, okay, which I want to use. So this sort of connection, so what you're seeing here, this sort of connection will give us less number of connections and wires to be used. So the intention behind the shorting of all these lines, all these individual segments of all the 7 segment display LEDs, and using the common A bar to G bar and DP lines is to have the lesser use of connections. So this sort of connection will lead us to lesser number of wires to be used. So if I have a 4-digit, then I need here 12 signals. Okay, so because 8 signals here, so plus these four signals. Okay, 8 plus 4 equal to 12. So by having 4 digits, I need only 12 number of signal lines. Okay, therefore I can have 8 into 4 equal to 32 connections I would be using for 4 digit, and A0 bar to A3 bar were not used in that case. Okay. So now by using this, I will be in need of only 12 signals. Okay. Again, why 12? Like this A0 to G bar along with one DP, 8 signals plus A0 bar to A3 bar, 4. Okay. 8 plus 4 equal to, like this 12 signals are enough. So all the 4 digits will be used at a single stretch only. Okay. So for this, we have this scan mechanism. So where one by one means each A0 bar, A1 bar, A2 bar, A3 bar will be made low, right? And the digit will be displayed. So, but this happens like in a very much fast fashion. Okay. So this it will be happening at a faster rate so that the user will not be able to sense this or feel this. Okay. So this scanning will be happening at a much more faster rate and the user will not be able to like observe this. Okay. So due to the persistence of vision, like what you call it as, okay. So due to the persistence of vision, so where the human eyes will not be able to sense this much faster fluctuation. So hence we see that all the 4 LEDs will be glowing with different values on it. Okay. So you can explain these concepts for 7 segment displays. So next one is uh, LCDs. So these LCDs are nothing but liquid crystal displays. Okay. So these LCDs will be acting as an alternative for the use of LEDs for displays. So some systems will be using the LCD displays where each segment of the LCD consists of a liquid crystal material between two optical polarized filters. So the liquid crystal also polarizes light, and it depends on the angle of polarization, so which allows light to pass or to be blocked by the filters. Okay, so the main advantages of these LCDs when compared to the LED output devices are like these LCDs are able to consume low power and also readable in bright ambient light conditions and custom segment shape. So like these LCDs are available at different shapes, and the main demerit is like this LEDs requires backlight for dark conditions, not as robust when compared to the LEDs. Okay, so these LCDs require ambient light to be visible, and the main demerit disadvantage is like in low light conditions, a backlight is needed, which is one of the main disadvantages. Another disadvantages include the mechanical breakability and a smaller range of temperature over which they can operate. Okay, so you can mention these details for LCDs. So next one is actuators and valves. So now let us see the actuators and valves. So like here we have the actuator used to cause, okay. So the actuator used to cause some mechanical effects in a solenoid, like as shown in the figure, okay. So now let us see this mechanical type of output device. Here we see this electrical to physical causing devices. For example, so we need to have the control a movement of valves, or like I want to control the on and off of a valve. Okay, in such cases, you need to have the control the flow of liquid. So, for example, okay. So for such cases, we can go for the use of these actuators. Okay, so these actuators are used to cause the mechanical effects in a like is a solenoid. Okay, so with no current flowing through the coil. Okay, so you can see here. Suppose if this so suppose if the coil is not fed with any flow of current through the coil, the spring will be like as you can see here. So this spring will be able to hold the steel armature okay, out from the coil. And when the current is flowing, so this coil will be able to act as the electromagnet, and so this will be drawing the armature in against this particular spring, okay, this particular spring, okay. I repeat, so with no current being fed to the coil, so with no current flowing through the coil, so this spring will be able to hold the armature out from the coil. And so when the current is able to flow, so then this particular coil will be able to act as an electromagnet, and so this electromagnet will be able to draw the armature inside against the spring, okay. So this solenoid is nothing but an electromagnet basically, right, in which if the current is flowing in the coil, it behaves as a magnet. So you can see a so you can see the spring here, okay. So we see a spring, so which will ease its motion, okay. See this valve is closed. I mean, suppose if this valve is closing, so for opening a valve, we must make the current to flow in this particular coil. So the spring is pushed, okay. So this spring is attached to the coil, hence the valve is opened. Therefore, a solenoid can be used to open or close a valve, right? And we know that a valve can be used to control the flow of liquid, etc. So this valve remains eventually closed, okay. Therefore, for opening a valve, we need to pass the current, okay, solenoid, right? Hence, you can open the valve, okay. You can see that so we have a linear motion. So this linear motion is created using a solenoid, and if we attach a lever to this, so then I can also translate this movement so as to control other physical things, okay. And if you can call it as an actuator, why? Because this is actually implementing the physical commands, okay? So the diode, so what you can see, yeah, right. So like here you can see like the two important classes of devices used on solenoids. So the first being the solenoid valve, so which can attach the armature of a solenoid to a valve mechanism, allowing the solenoid to open and close the valve. So thus we can have the controlling the flow of, say, some liquid or some gas, okay. So this gives us means of controlling the chemical processes and other fluids, okay, like in the process-based systems. So you can have a control of some parameters like fluid flow, gas flow, etc. Okay, so you can explain this with this particular figure, okay, electromechanical actuators and valves. So next is the motors. Like I'll be continuing the next class like on motors. Okay. Till then you can revise these things, right? Thank you.